For the sake of the video, I've gone over my circles in Biro, so you don't need to do that obviously, but it shows up a little bit clearer. So the theorem that we're looking at, Theorem 19, it says that the angle subtended at the center of a circle, so this is the angle at the center of a circle, that's what this is called, is always twice the angle at the circumference. So that is, if I connect this point here to any other point on the circumference. Okay, now can I just point out that the 3 points I've chosen here are completely random. You can choose any 3 points you want. You should find the same result. And just to measure what we have here, let me just rotate this. Okay, this angle here is 70. Okay, I'm going to put that at 74 degrees. So if that's 74 degrees, our theorem says that's twice as big as this angle here. So when we measure this, half of 74 is 37. That's what we're expecting. Let's see what we get. Line that up at 0, 30, 5, 6, 37. Okay, so that's a 37 degree angle. And you may not have had the same angles, but you should have found that this one is twice as big as this one. So the angle at the center is twice the size of the angle at the circumference. That's the theorem, and we'll be proving that at a later point. The corollaries are things that just come straight from that. So one of them is that if you pick 2 points on the circumference and you draw any 2 angles to another point, okay, so there's one angle and here's another one, that these 2 angles have to be the same size. So the measurement of that, if you want to measure it, you can see that my first angle there is again about 38 degrees. My second angle here, again, also 38 degrees. So those are the same size, and the reason for that is because both of them are half the size of this angle here, as long as they stand on what's called the same arc. So just in red here, because they're both standing on this arc here, I can say that they are equal angles. So angles that stand on the same arc are equal. A second point is that what's called a cyclic quadrilateral, that is a shape that has 4 sides that will fit inside a circle, will always, and it doesn't matter how kind of random or irregular the shape appears, as long as the 4 vertices of the shape land on your circle, all 4 angles, the opposite angles will always add up to 180. So that this angle here and this angle here together will give 180. Again, just measure that in your own diagram. You'll get different answers to me, but I have what looks like 94, 95 degrees for this one, and this one up here is just shy of 90. It's about 92. Okay, now I probably haven't drawn that perfectly, so I'm finding that it adds up to just under 180. The reason we can say with confidence that it's 180 is this. Again, if we connect the 2 points on which those angles stand to the center. Okay, so this is almost a straight line, which is a bit of a pity. It's not too clear maybe. This angle is going to be half of this angle, and this angle here is half of this angle by our theorem. So because these 2 angles add up to 360, these 2 angles add up to half of that, 180. Okay, another important point, our corollary, is that if I put a straight line through the center, which we nearly saw with our quadrilateral just now, if I draw a diameter, any angle which stands on a diameter, well, if that's 180, this is half of it. It has to be 90 degrees. So let's check that. Again, in your drawing, check your set square. There it is, perfect 90 degrees. And another corollary which is related to that is if I draw a 90 degree angle from the side of my circle, so if I have, if the angle upon the circumference is 90 degrees, then the line that connects those two points on the circle must be a diameter, that is, it must go through the center. Again, just due to maybe slightly sloppy drawing, it's not quite going through the center, but it's pretty close. So that's Theorem 19, and its 4 corollaries, or the 4 ideas that flow straight from it. So if we examine question 6 here from 16.2, the measure of the angle marked with the letter in each of the following circles. Well, A here has to be half of 126, and half of 126 is 63. B is half of 92, so that's going to be, what's that, 46. C here has to be twice 59. That's the angle at the center, so that's 118. From our corollary, 32 and D have to be the same size. 98 and E have to be, 78 and E have to be the same size. And if that's 206, half of that is 103. Okay, again, angles on the same arc. They're standing on this arc here, 21 and 21. Angles on the same arc, I and 62 stand on this arc, so they're the same. 47 and H stand on this arc, so they're the same. Here, 7 is asking about cyclic quadrilaterals. Remember, the opposite angles add up to 180. So 45 plus D have to give 180. So D is 135 plus 45. E here plus 104 add up to 180, so that's 76. Okay, I'm going to ask you to look at those questions and do them into your copy, so I won't write them down. Question 10 is important for this reason. The X is easy. Half of 100 is 50. The Y is a bit trickier, but if I draw this line here, I can say, well, I have an isosceles triangle. So that's 30 and this is 30. If that's the case, I know the whole thing is 50. This is 20. And Y has to be 20 as well. Okay, and that's going to be an important idea that comes up in the theorems. I'll leave it to you to try the rest of 10, but this one certainly involves, you need to draw in that extra radius there and work with isosceles triangles for 10 part 2. 10 part 3 does not require that, but you can give that a go as well. So I want to examine question 4 here and question 9 in a little bit more detail. So in this given circle here, you've got A, B, C, and O is the center. Why is OA the same size as OB? Why can we say that? The answer is they're both a radius. Okay, so I've got the diagram here. OA and OB are both a radius of the circle. So AO equals OB because it is the radius. Okay. Therefore, what is the angle? What is the angle ABC? Well, you know, if this is 180, half of that is 90. That's one of our corollaries. So that's a 90-degree angle. We'll just say corollary to Theorem 19. If you can't remember the numbers, you can just say half of 180. ABO, that angle there, but this triangle here is isosceles. You've got two equal sides, so that has to be a 30-degree angle. A 35-degree angle, excuse me. Same as this angle here. So ABO is 35 degrees because isosceles triangle. OBC then is 90 take away 35 gives 55 degrees. And the last OBC, is 55 degrees because it's 90 take away 35. They also ask in the question, explain why the triangle OBC is isosceles. It's because two sides in the triangle, this side and this side, are radiuses. Okay, so that's your two equal sides. Sorry, two of the sides are radiuses, so that's your two equal sides, which means if that's 55, this is 55 degrees as well. And you can fill in now the rest of the angles if you wanted to. 55 and 55 is 110, which makes this a 70 degree angle. 35 and 35 is 70, which makes this a 110 degree angle. And you can see there you've got 180 in your straight line. Question 9 gives you this diagram here. It says, in the given diagram, O is the center of the circle. The angle AOB is 140 and OAC is 30 degrees. Find ACB. ACB, well, that's half of 140 is 70, so that's equals 70 degrees by Theorem 19. The angle OCA, now that line's not drawn in, but if we drew it in, it's from the center. That's a radius, okay? And this is a really important idea when we come to proving this theorem. We draw in that radius and you get yourself an isosceles triangle. So now you can say, well, OCA has to be the same as this 30 degrees here. Okay, so that's a 30 degree angle because the triangle AOC is isosceles. The angle OCB, well, we know that ACB is 70, take away that 30 leaves 40 degrees here. Okay, so that's going to be a 40 degree angle, and that's just because it's 70, take away 30. And finally, the angle OBC, well, if that's 40, and this again is an isosceles triangle because you've got two radiuses, that's 40, and this will be 40 degrees as well. Isosceles. Okay, so there's question 9. We're going to finish with question 17, which gives us this diagram here, and it says prove that the triangle AXB and CXD are similar. Similar, if you remember, means all three angles are the same, which then means the corresponding sides are in proportion. It's enough to get two angles, because if two triangles have two angles in common, the third one must also be in common. So this one, we're going to say, well, these are vertically opposite angles. Okay, AXB and DXC are vertically opposite, so they're equal. And we can also say that BAC and BDC, because they stand on this arc BC, they must be equal. Similarly, because ABD stands on this arc AD, it must be equal to ACD, okay, because they stand on the arc AD. Okay, that's called a minor arc, where it's the short one. The major arc AD goes around from here to here. Just if you hear that language, that's what that means. So proving it, you're going to start off by saying, well, the size of the angle AXB is the same as the size of the angle DXC. That's because they're vertically opposite. Then you're going to say also the size of the angle BAC is the same as the size of the angle BDC because they stand on the same arc. So you can say therefore three angles in common, and that is they are similar triangles. Okay, if you wanted to show the third one was equal because they stand in the same arc, that'll be fine too, but there's enough there. Okay, we'll leave it there.